Okay, good morning, everyone. So again, we are approaching towards the end of the semester, and today we'll learn a new algorithm, actually, not any revision, max flow, and which is slightly tricky, trickier than other algorithms. And in many cases, if you see YouTube videos, many videos are wrong actually. So, yeah, means they do not follow the whole algorithm. Partially, it's correct. Okay, so we'll go through this algorithm today, and I will use my iPad. So please join me over Zoom. Join me over Zoom, and we'll discuss the algorithm step by step. Can you see my screen?
Yes, yes.
Okay. So the problem is maximum flow. The problem is pretty easy to understand. Let's take one example. This is source node. Okay. Now, there are two special nodes here. One is source node, another one is sink node. Okay, source and sink. You may think this is your house. Just assume this is your house, and there are multiple pipelines for water connection. In your apartment, just assume this is so this is your apartment, just think. And there are multiple water connections. Okay, so all edges you may consider as pipe. So this edge weight, 13, 14 or something, in case of shortest distance, the edge weight represents the cost of each edge. Here, each weight is the capacity. It represents the capacity of a pipe, you may consider. That means this edge from S to V2 can carry 13-gallon water at a time. Just think of that capacity, okay? Maximum capacity. So this all edge weights are here, capacity. In case of shortest path, it was cost, okay? So there are many pipelines, like this pipeline can carry 20 gallon of water at a time. This one is 4 gallon of water. So just think of pipeline. So the goal is you need to flow as many liquid as possible from source to the sink node or to your apartment. Okay, you can explore all edges as many as possible so that maximum amount of liquid will be flown from source to your apartment. So what do you think? How you can do that? You don't need to apply computer science. Means you can choose any path, then supply as much as possible. Okay, let's take one path. By the way, what is path? What is path? Yes, in this case, it is source to target node, and some path would be, it will go through some vertices from source to your target node. So one path can be S, V1, V3, target node. This is one path, right? Now S to V1, the capacity is 16. V1 to V3, the capacity is 12. V3 to T, the capacity is 20. Now tell me how much actual liquid that you can flow from source to target through this path. No, think about the pipe. So this is one pipe. This is another pipe. This is slightly larger pipe. 12. Why 12? So that means you are taking the minimum of them, right? Minimum of 16, 12, 20, the minimum capacity. Is it clear why 12? Yeah. So through this path, you can flow maximum 12 gallon of water, maybe. Clear? So tell me, what is the relation between flow, actual flow, and capacity? What do you think? It is flow 12. In this, for this pipeline, the capacity was 16. For this pipeline, the capacity was 12. For this pipeline, the capacity was 20. What do you think? What is the relation between flow and capacity?
Capacity is the maximum that flow can be in a given pipe, but flow is what actually gets through.
Yeah, what is the relation? Means who is larger? Flow or capacity? Who is larger? Capacity. So make sure to remember flow would be always smaller than capacity. Smaller or smaller than equal. If flow is more than capacity, that means there is a leakage in your pipeline. And we will not consider that. Okay? So never flow can be more than your capacity. It would be always less than or equal to, maximum equal to capacity. So this is one constraint. Okay? Flow should be always smaller than capacity. Clear so far? So we can supply 12 gallon for this path. So we can also utilize other paths to supply the same liquid from source to the target node, right? Because the other paths are empty so far. Is it clear? So we can use the other path like S, V2, V4, T. That path is empty right now. So we can supply another amount of water through that path at the same time. So, okay, this is flow 12. Then we can use another path S to V2, V2 to V4, V4 to T. What is the capacity from S to V2? 13. V2 to V4, 14, V4 to T4. So what is the actual flow? 4, the minimum one, right? Is it clear so far? Are we done, or can we send more water? Is there any path left that we can utilize? What do you think? Our goal is to supply maximum amount. So that's the goal. So we have used as V1, V3, T, this path, and through that path we supplied 12 gallon. And we used S, V2, V4, T, this path, and we supplied 4 gallon of water. Is it the maximum, or can we use some other path to send another amount of water? Great. So S, V2, V4, V3, T, right? So S, V2, V4, V3, T. This is also a path. Now, what would be the flow in this path? Remember, we have already used a couple of things like V3 to T, this path, we are already using 12 gallon. We are already providing 12 gallon water through that path. Also, we are using through this edge, we are also providing 4 gallon of water because of this path, right? So what things you need to keep in your mind when you calculate flow for the third one? We need to also consider those things, right? So what will be the maximum? So S to V2, we have already used 4. We have used the capacity. So remaining capacity would be 13 minus 4, right? So 9. V2, V4. Previous capacity was 14. We have used 4 for the second path. So the remaining capacity is 10. V4 to V3. It is untouched so far. So the capacity is as it is, 7. V3 to T, what is the remaining capacity? What is the remaining capacity? 8, 20 minus 12. Right? And what is the flow in this path? The minimum one, 7. So what is the maximum flow from source to terminal node? So the maximum flow would be the summation of this 12 plus 4 plus 7. So 23. So 23 gallon of water you can send or you can supply at a time from source to terminal node. So is it clear the problem? What the problem we are dealing with? Clear? Now it is easy for the small graph to choose the best path, but programmatically it is not that easy to choose the best path, right? Okay. So what we have learned so far? First, each edge has some capacity and you cannot flow more than that capacity. So flow would be always less than capacity or less than equal to capacity. So you cannot flow more liquid than the capacity of that pipe. It makes sense, right? Next is, here we have assumed that a particular node, maybe you may think V3 or V2 or something, whatever they intake, whatever amount of liquid they intake, they will not reserve anything with it. They will, so take any node V1, whatever amount it intakes, suppose 10 gallon of water, it will also release the same amount of water. maybe through 2 pipelines, it is 8, it is 2. So it will not conserve any amount with itself. So this is flow conservation. That is the rate at which liquid enters a vortex must equal to the rate at which it leaves the vortex. So these are assumptions. So there is no traffic, there is no blocking in your pipe, there is no leakage in your pipe. These are some assumptions. Okay. So this flow conservation is the amount of water inserted is inserting to this vertex V1 at which at a particular rate it will be the same vertex V1 will leave that same amount with the same rate. So it will not hold any amount of water with itself. So this is flow conservation. So the amount you will pass, you will send to V1, the same amount will be released from V1 at the same rate. So no blocking. So these are assumptions. Okay. And you may think this example for liquid, you are trying to send gasoline from a source to a gas station, or you may think you are supplying, like just think in real case, Walmart have now workstation in some remote area, and Walmart wants to send supplies from that workstation to its Walmart shopping center. And there might be multiple paths. So they can send multiple trucks through different paths so that they can send maximum amount of supplies within a certain period of time. Or you can think of electricity. So your government is sending electricity from maybe Birmingham to Montgomery through different channels. And their goal is to send maximum amount of electricity within a period of time, at a time. So basic, you have understood the problem, right? The max flow. So the goal is to send or supply maximum amount of liquid or electricity, whatever it is, from source to sink node. And there are two special kind of nodes, the source node and the terminal or sink node. And here we have assumed that there are another assumption is that source node have unlimited capacity, means unlimited amount of liquid. There is no limitation. So source node has unlimited amount of liquid and it can send unlimited amount based on the capacity of the pipeline. So don't think that source node will not have the supply of liquid. Don't think about that. These are assumptions. So this is the max flow problem. So this is special node source, and this is terminal node, or you may think sink node. So let me write the goal. So the goal of the maximum flow problem is to compute the This is the goal. Just go through this goal and we'll briefly discuss this goal again. So the goal of maximum flow, this problem is to compute the greatest rate. Why we are saying it is rate? Means we are supplying some amount of water at a time. Okay, it's not that we are so from source to this sink node, we supply 23 gallon of water at a time. So time is also considered here. That's why it is rate. So you may think 23 per hour or something, 23 per minute or something. So that's why it is rate. So the greatest rate for shipping material from the source to the sink node without violating any capacity constraint. Capacity constraint means your flow cannot be more than your capacity. At the same time, that flow conservation rules should be applicable. So those are capacity constraints. So goal is you need to supply maximum amount of material from source to sink node without violating any constraints. That's the problem. Okay. So there are two terms, that is flow and capacity. So for each node, we need to track both of them, flow, capacity. So we'll use like this, flow / capacity. It's not division, okay? It's not division. We'll, for every edge, we'll track flow as well as capacity because we need to know the remaining capacity. And we'll, based on that remaining capacity, we'll increase the flow. So we need to track them. So this way will represent flow and capacity for every edge. Okay. Now, here we will apply Fulkerson method to find out Fulkerson method to find out the maximum flow. So this is the method that we are going to apply. So it is very easy to find the maximum flow and okay. We have used a couple of unknown terminology here. Okay. So what is the method? It is saying that it will repeatedly find the augmenting paths through the residual graph and augments the flow until no more augmenting paths can be found. So we'll discuss every terminology one by one. Okay. First, augmenting path. So right for now, you can think for every time here we have found one path, right? We have found one path, and augmenting path means how you can find one path. When you find one path, what things you considered? Or in other words, why you have not found another path after considering these three paths? Why not you choose another four paths? Why you stop here? No more path with no more valid path, or you may think no more path with capacity more than some value, right? So augmenting path means path with capacity more than zero. If there is a path that you can supply some material through that path, which is not full, means augmenting path is path which is not full. If it is not full, then you can supply some material through that path, right? So augmenting path is path. So first discuss augmenting path. Path of edges in the residual graph with unused or remaining, let's use unused capacity, which is the remaining capacity greater than zero from the source to the sink. Okay. So augmenting path is nothing but a path which is not full yet. So there is some empty space. So you can utilize that space. So that is augmenting path. That's why it is saying unused capacity is greater than zero. It means it's not full yet. Maybe partially it's full, but not completely full. Okay, this is augmenting path. Now, talk about the augments the flow, the third one. Augments the flow. What does that mean? Here, you calculated flow for path 1, right? Then path 2, then path 3. And what you did at the end? Max 1 means augment the flow means you will update the flow every time you discover an augmenting path. So first, your flow is 12. You find another augmenting path, then the flow becomes 12 plus 4, that is 16. Then you find another third augmenting path and flow becomes 12 plus 4, 16 plus 7, that is 23. So every time if you find one augmenting path, you will update the max flow. So initially maximum flow is 12. Then you find one path 2, your maximum flow becomes 12 plus 4, that is 16. You find path 3, then you modify, update augmenting flow, max flow to 16 plus 7, 23. So augmenting the flow means you will update the max flow after discovering an augmented path. So means updating the flow okay. At the same time, this part will be cleared when we'll take another example. Means every time, suppose this one, let's take this example. when you consider path 1 from V3 to T, the flow was 12, right? When you consider path 1, V3 to T, this one flow was 12. So let's write this way. So flow was 12, capacity was 20. Then when you consider path 3, this one, so V3 to T, the flow becomes 12 plus what? When you consider path 3, how much amount you supplied? 7. So the flow becomes 12 plus 7, 19. So this is augments the flow. So you augments the flow for this age. Previously it was 12. When you consider only path 1, you consider path 3, and then you update the flow for this particular age. And it becomes 12 plus 7, 19. So 19 gallon of water you are sending from V3 to T, while the capacity is 20 gallon. Okay, we'll take example, it would be clear. And finally, the residual graph. It is graph containing residual edges. Now, residual edges means, what is the meaning of residual or residue? What is the meaning of residue in English? Leftover, remaining. So when you consider one path, you need to check the remaining capacity, right? So residual graph will consider the remaining leftover capacity. So after considering path 1, when you choose path 3, you need to calculate this remaining capacity, right? Always you need to track the remaining capacity because it's partially full. So residual graph will track that remaining capacity, leftover capacity. Okay, let's take one example, then it would be clear. Okay, I know it's lots of theory. Let's take one example. Okay. So the example. Okay, this is the graph which is given. Now we need to find the maximum flow using Fulkerson method. Do you know that this is the graph I have drawn here on my iPad note? Now, can we copy this graph multiple times? How? Because I have to draw it 10 times now. So if I can copy paste, then it would make my the thing easier. I don't know. I don't know. Okay. So this is the graph which is given. Okay. So first thing would be we need to find, okay, initially this is the graph and you are not sending any liquid. So what is the current flow? 0. So assume that in the beginning the flow is 0. Okay. So we'll first draw the residual graph. So from this point, we'll draw the residual graph. So I need to draw the same graph again. Okay. Now flow is 0 for every edge. So 0/16. That means it is saying that capacity is 16, flow is 0 initially. 0/13, 0/4, 0/12, 0/9, 0/14, 0/4, 0/7, 0/20. So
Touch and hold and drag to expand the selection.
really touch and I can't select.
Is it because you're on a pen? Oh, there it goes. Remember you just did.
Okay. Yeah. Yes. Hopefully it, but how to copy? No, I'm not getting. Yeah. Oh, copy. Yeah. Test. Oh, yeah. Thank you. Thank you so much. Okay. Okay. So initially flow would be 0. And what is the meaning? This is the flow and this is the capacity of the edge. Okay. Now the good thing of this augmenting path we'll discuss right now. The good thing is if you choose, okay, in the first example we have chosen the best path. Okay, but if you choose the bad path, so what will happen? So there should be some process to undo my bad selection, right? So if you choose a bad path initially, suppose you have chosen S V2, V1, V3, T, or you choose S V1, V3, V2, V4, T, then you will see you will not get this 23 value. So if you have chosen a bad move, how you can undo that process? So Fort Fulkerson will show you if you choose randomly, because you cannot solve it manually. When you do programmatically, any path, any augmenting path can be chosen. So if it is a bad move, then the method will undo that process. So it is guaranteed that you will always get the maximum flow at the end when the algorithm terminates. Okay. So this is the residual, the graph with flow and capacity. Now we have chosen one path. So let's assume the path that we have chosen is path 1 is S V1, V3, V2, V4, T. S V1, V3, V2, V4, T. Actually, it's a bad path. Okay. So S V1, V3, V2, V. Okay, V4 is V4, T. And S2 V1, the capacity or remaining capacity is currently 16 because the flow is 0. V1 to V3, it is 12. V3 to V2, it is 9. V2, V4, it is 14. V4 to T, it is 4. So how much actual liquid that you can flow through this path? what is the amount? 4, right? So that will be called bottleneck. Bottleneck of an edge. Bottleneck means that is the maximum that you can flow, right? You cannot flow more than that. So that is the bottleneck of that edge. So we'll track that bottleneck. So bottleneck of this edge would be minimum of 16, 12, 9, 14, 4. So that is 4. So that is the bottleneck. So we need to track this bottleneck. So the current max flow, currently after choosing path 1, my max flow becomes 4. Previously it was 0. We have just started. Previously max flow was 0. It becomes 4. Clear so far? So if flow is 4, so we need to update this graph. So it becomes 4. Then we have chosen only this path. Everything else would be same, no change. Only through this path or through this path of edges, we need to modify the flow. So it becomes 4, it also becomes 4, it also becomes 4, it also becomes 4, this one becomes 4. Clear so far? Now the major point. What happened? Okay. Now what we'll do, we'll draw the residual graph. This residual graph from this point, from here, we'll draw the residual graph, corresponding residual graph. Okay, how to do that? So I'm omitting the edges throughout the path that we have chosen. Rest would be same, no change. Okay, so S to V1, what is the current flow? S to V1, what is the current flow? 4. And what is the remaining capacity of that edge, S to V1? 12. So in residual graph, we need to track 2 things. What is the remaining capacity that I can utilize in future? And second is, I have already used 4 amount of 4 out of 16. If that is a bad move, I should be able to undo the process, right? So 2 things, remaining capacity and whatever I am currently using, I should be able to backtrack or undo the thing. So here 2 edges will be drawn. One would be this forward edge, that is the remaining capacity, that is 16 minus 4, that is 12. It is saying that I can utilize this 12 unit throughout this edge. That is the remaining capacity I can utilize in future. And if it is a bad move, then I will undo. How much? How much? That depends on the currently using amount. So what is the current flow? 4. So I can undo maximum 4 unit. That is back edge. Means if I need to undo, then I can undo 4 unit throughout this edge. So this is the remaining capacity, 12, and 4 is the currently I'm using. If I need to undo the step, then I can undo maximum 4 unit throughout that edge. It is clear? Similarly, V1 to V3, what is the forward edge? V1 to V3, forward edge is the remaining capacity. So 12 minus 4, 8. Is it clear so far? So what is the back edge? That means how much you can undo. 4, right. Now V3 to V2, what is the forward edge? V3 to V2. 9, right. No. 5, right. 9 minus 4, that is 5. The remaining capacity, that is 5. Now, what is the back edge? 4. Now, V2 to V4, what is the forward edge? 10. 14 minus 4, that is 10. Forward edge means remaining capacity. Just take it as a note. Forward edge means remaining capacity, and back edge is the amount that you are currently using. Means your flow, actual flow. Now, what is the back edge from V2 to V4? That is 4. Now, V4 to T, what is the forward edge? 0. Please note, pay attention here. V4 to T, the forward edge is 0, means there is no capacity left. It is fully occupied. So only back edge would be there, no forward edge. And back edge would be 4. So it is illustrating that the edge is all fully occupied. Clear so far? Means this edge is saturated. You cannot utilize it next time. It is already saturated. So only back edge. So clear so far? Okay. Now, okay. So now we'll continue from this residual graph. From this residual graph, we'll find augmenting path. And what is augmenting path? Path with remaining capacity greater than 0. Okay. So we'll utilize this graph. So if I draw, copy it. Why it is taking? Yeah. Okay, so let's draw a line here. Now we'll choose a second path. Okay, next let's choose path 2. Is V2, V1, V3, T. So S V2, V3, V2, S V2, V1, V3, T. Yeah. And we'll use this graph. So can I copy it? Oh. Don't know. Okay. Just I'm drawing the previous residual graph so that you don't be, I am not modifying this one so that you become confused. I'm drawing it separately. Yes. Now we have chosen S, V2, V1, V3, T. So what is the bottleneck? So bottleneck would be minimum of their remaining capacity. So S to V2, what is the capacity? S to V2. What is the capacity? S to V2? 13, yeah, it is unused. Next, V2 to V1, what is the capacity? 4, unused. Next, V1 to V3, what is the capacity? What is the capacity? V2 to V1 to V3? 8. Only think about the forward edge because we are already calculating that remaining capacity. So you don't need to do anything else. Just check the forward capacity, forward edge weight. So it is 8. Then V1 to V3, then V3 to T. 20. Yeah. So what is the minimum? 4. So this is bottleneck, right? So if we choose path 2, then bottleneck is 4. So what is my current max flow? So you need to modify max flow. Previously it was 4. Now 4 plus 4, that is 8. So my max flow becomes 8 at this point. So now let's draw the flow. So here we have chosen this path. First draw the path. So this is the path that we have chosen. And so modify the flow. So it is 4, it is 4, it is 4, it is 4. Okay. So draw the corresponding residual graph. So let's draw it. S, V1, V2, V3, V4, T. And when we draw the residual graph, only the path that we have considered will be modified. Rest would be as it is. So S to V1 would be as it is, no change. 12, 4. This is same as it is, no change. This is same as it is, no change. This is as it is, no change. This is as it is, no change. Oh, I make mistake here. I think, yeah, this would be the direction would be this way. This is back edge. So this is back edge, like 4, forward edge with 5. Yeah. So these are untouched. So just copy as it is. Now we need to modify this part. S to V2. S to V2, what is the forward edge? S to V2. What is the forward edge? 9. That is remaining capacity. Keep that in your mind. Forward edge means remaining capacity. Back edge means your current flow. So S to V2, the forward edge is 9. 13 minus 4, that is 9. And S to V2, the back edge is, what is the back edge? 4. We are currently using 4. So it is 4. Okay. Now V2 to V1, what is the forward edge? V2 to V1, 0. That means it's fully occupied. So that means V2 to V1 is saturated. So only back edge, no forward edge. Is it clear so far? Next, V1 to V3. What is forward edge? Forward edge means remaining capacity. 4. 8 minus 4. So it is 4. So what is the back edge? V1 to V3. 8. Previously it was 4. Now 4 plus 4, that is 8. Now V3 to T. What is the forward edge? 16. And what is the back edge? 4. Clear so far? This is my residual graph. Same thing we need to repeat. We will repeat until we will not get any augmenting path. Until we get any augmenting path means remaining capacity is more than 1. Means forward edge in the residual graph will have capacity more than 1, more than 0. Until we have that, we need to repeat the same thing. So let's take another augmenting path, path 3. Suppose this is S, V1, V2, V3, T. Okay. Now, what is the bottleneck? Okay, first let's draw this one. Can I copy this? S, V1, V3, P, V2, V4, 9, 4, 10, 4, 4, 0, 60, 4, 8, 4, 12, 4. So we have chosen path 3. So what is the bottleneck of this path? Would be minimum of S to V1. What is the capacity? S to V1, 12. Then V1 to V2, 4. Then V2 to V3, V2 to V3, 4. V2 to V3, the forward edge. from V2 to V3, that is 4. And then V3 to T, 16. So what is the minimum? That is 4. So I need to modify my max flow. So max flow equals to, previously it was 8. Now 8 plus 4, that is 12. Yes.
Forward edge from V2 to V3, so shouldn't that be V3 to V2?
V2 to V3. V2 to V3. Yeah, there is.
But that's a back. Is what I'm saying, 'cause we put that earlier.
Yeah, that's why you are on the right track. Even you can think V1 to V2. V1 to V2, because we are considering only residual graph, and this way, initially the path 1 was a bad move. We are in the process of undoing the bad move. This is the process. Yep, but thanks for pointing out. So although we have chosen a bad move, this is the process when we are undoing that thing. Yeah. So this is max flow. Okay, that is 12, and bottleneck for this edge is 4. So which path we have chosen? S2 V1, then V1 to V2, then V2 to V3, then V3 to T. And throughout that process, flow is 4. So draw the corresponding residual graph. So this would be 8, and the back edge would be 4. Now draw 9, this is 4. 10, this is 4. And this is 8. Now notice, previously V1 to V2, V1 to V2, what is the forward edge? V1 to V2. 0. That means it is fully occupied. It is saturated. That means we will have only the back edge with flow 4. So we have, this is clear? Okay, so back edge. Now V2 to V3, V2 to V3, what is the forward edge? That is the remaining capacity. 4, 0. So the whole thing would be, let me erase, the whole thing would be the back edge. So this is the back edge, right? With capacity 9. So that, see, we have chosen, path 1 was chosen as a bad move. Now we came back, we have undoing the same thing. Initially, just go through that initial path. See this one. We have get back to that point. Although we have chosen a bad move, we have undoing the process and came back to that move. Got the point? See, we have got this one. So 9, there is no forward path, and V3 to T. V3 to T, what is the forward edge? V3 to T. V3 to T. What is the forward edge? 4 is the flow, 16 is the capacity. 4 is the flow, 16 is the capacity. What is the remaining capacity? 16 minus 4, 12. Yeah. And what is the back edge? 8. 4 plus 4, that is 8. Clear so far? So this is after considering path 3. Any questions so far? Okay. So we are done with path 3. Let's consider path 4. It is, let's become SV1, V3, T. So I'm running out of time. So what is the bottleneck of this path? S to V1, the remaining capacity is 8. V1 to V3, it is 4. V3 to T, it is 12. So bottleneck is 4. So my max flow would be, previously it was 12. So 12 plus 4, that is 16. Max flow becomes 16. Now we need to, so I'm modifying this graph to save time. So we have considered this path S to V1, then V1 to V3, then V3 to T. So 4, 4, 4. Okay. So I'm drawing the residual graph, corresponding residual graph. So it will become S, T, V1, V3, V2, V4. So it will, the remaining capacity would be 4, the back edge would be 8. Here 4/4, that means there is no remaining capacity, so only back edge, that is 12. Here remaining capacity 8 and back edge is 12, and rest would be as it is, no change. So this is path 4. Now path 5. So let's assume we have chosen S, V2, V4, V3, T. What is the bottleneck? Minimum of S to V2. What is the remaining capacity? S to V2? 9. Only see the forward edge weight. S to V2, we are choosing this path. S to V2, then V2 to V4, then V4 to V3, then V3 to T. We are choosing this path. So the bottleneck would be 9, 10, 7, 8. So the minimum is 7. So max flow, previously it was 16, 16 plus 7, that is 23. So corresponding residual graph would be S, V1, V3, V2, V4, T, 4, this is 4, this is 4, this is 8, 12. Yeah. So this, what is the forward edge? S to V2. S to V2. 9 is already there. I am using 7. 9 minus 7, 2. And what would be the back edge? 7 plus 4, 11. V2 to V4. What is the forward edge? 3. 10 minus 7. What is the back edge? 11. Now V4 to V3. Will be there any forward edge? V4 to V3. No, because the edge will be saturated. So only back edge. Now V3 to T. What is the forward edge? 1. And what is the back edge? 19. Okay, this is my current residual graph. Now see, there is any possibility to choose any forward any augmenting path with capacity more than 0? Is it possible? Now notice this path is saturated, back edge, only back edge. This path is saturated, only back edge. This path is also saturated, only back edge. So is it possible to choose any augmenting path? No. So stop the algorithm. So what is my current max flow? 23. So this is the answer. Clear? So this is the Fulkerson method to find out the maximum flow. And you have understood, if you have chosen a bad move, how Fulkerson can undo that process. So it is guaranteed that you will get maximum flow when the method terminates. So any questions? Don't you want?
No.
Yeah, lots of work.
It's gonna be the entire month.
Really?
So unless it's a one question final.
Actually, one question final.
No, you need to spread the points out.
Okay.
I've had one question final. They're no fun.
So you have understood the process, right? Just go through this again. And what many YouTube videos are doing, they are not considering this undoing process. They will only choose couple of paths and calculate the flow. But the process of undoing is the major thing, that you can choose any path, but if it is a bad move, this method will undo that process. And the next day, it's not done yet. Next day, we'll briefly see the shortcoming of this method, the problem with this method, and how another algorithm will overcome that problem. But we'll not go through this detailed example. It would be a very small example. Okay. Okay. Homework. One homework. Very small homework. Apply this Fulkerson for this graph.
What?
Yeah. Try to do this considering your first path 1 as is V1, V2, T, and path 2 would be is V2, V1, T in your residual graph. So first you will consider bad move. Okay. Choose the bad move, that is S V1, V2, T. Then, since it is a bad move, the method will undo the process. So next you will choose S V2, V1, T. And repeat the same thing. Path 1, path 2, path 1, path 2. See what will happen. In the residual graph, means you are undoing the process. Yeah, just try to do this. Then you will come to know the shortcoming of this method. Okay. We are out of time.